two corrections I want to make to the video on the sodium potassium pump. One very minor one, and I don't think it would trip too many of you guys up. But near the end of the video, as we learned, we have potassium getting pumped into the cell by the sodium potassium pump. Let me draw the membrane. It'll actually be useful in the more significant correction I'd like to make. So let me draw the cell membrane, a cross section of a cell membrane. And let me draw the sodium potassium pump right here. The sodium potassium pump. And we saw it pumps out 3 sodiums for every 2 potassiums that it pumps in. So it might look well, it definitely doesn't look like that, but it gives the idea. And we're pumping potassium ions in. So K plus, and we're pumping sodium ions out. And that's what the whole point of that video was. When this thing changes shape with ATP, it pumps out the sodium ions out. Now, the minor correction I want to make, and I don't think it would have tripped you up too much, is near the end of that video, I drew the potassium ions, and I wrote a K+, but a few times near the end of the video, I referred to them as sodium ions. And I don't want that to confuse you at all. It is potassium ions that are getting pumped in. 2 potassium ions get pumped in for every 3 sodium ions that get pumped out. So I don't want, even though I drew a K+, sometimes I said sodium by accident. Don't want that to confuse you. That is the minor error. The more significant error is that I said that the main reason that we had this potential difference, why it is more positive on the outside, than the inside. So this is less positive. I said that the main reason was because of this ratio. We're pumping out 3 sodium ions for every 2 potassium ions that we pump in. And I just got a very nice letter from a professor of physiology, Stephen Baylor at University of Pennsylvania. And he wrote a very interesting email. And it corrects me. And it's a very interesting, it's an interesting thing to think about in general. So here's what he wrote. And let's think about what he's saying. He says, here at Penn Medical School, we have a nice teaching program that stimulates the ion fluxes across a generic cell. So the ion flux is just the movement of the ions across the membrane, including that due to the sodium potassium pump, and that which arises from the resting permeabilities of the membrane. So the resting permeabilities is how easy it is for these ions to go through the membrane. We'll talk more about that in a second. And the resting permeabilities of the membrane to sodium, potassium, chloride, etc. One option our program gives students is to change the pump stoichiometry from 3 to 2. So when he's talking about pump stoichiometry from 3 to 2, he's just talking about they're changing the ratio. So they change it from 3 to 2 to 2 to 2. So what that means is they have a simulation program that says, well, what if the sodium potassium pump, instead of pumping 3 sodiums out for every 2 potassium it pumps in, what if it was even? What if it was 2 sodiums and 2 potassiums? And based on my explanation of why we have this potential difference, that should not lead to a potential difference if the main reason was the stoichiometry, the ratio of sodium being pumped out to potassium being pumped in. But he goes on to say, so they could change it to 2 to 2 in the simulation. As a result of this maneuver, the membrane potential, changes from its normal value of about negative 80 millivolts, and they measure that. They take the voltage here minus the voltage there, so that you get a negative number. This is more positive. It's a larger number. So it changes from negative 80 millivolts to about negative 78 millivolts. So what he's saying is, if you change this from 3 and 2, 3 sodiums for every 2 potassiums that get pumped in, if you change that to 2 to 2, it actually doesn't change the potential that much. You still have a more positive environment outside than you have inside. So that leads to the question, then why do we have the potential if the stoichiometry, if this ratio is not the main cause? And then, so it says it changes a little bit. It becomes a little bit the potential difference becomes a little bit less. The cell swells a few percentage, and then everything stabilizes. So then he goes on to write, so while it is true that the normal stoichiometry of the pump does have a slight negative influence on the membrane potential, that's just the membrane potential, the voltage across the membrane, the imbalance in the pump stoichiometry is not the main reason for the large negative membrane potential of the cell. Rather, Let me underline this. The main reason is the concentration gradients established by the pump in combination with the fact that the resting cell membrane is highly permeable to potassium and only slightly permeable to sodium. So we said in the last video, or the first video on the sodium and potassium pump, we said that there were channels. There were channels that the sodium could go through, and there's also channels that the potassium could go through, and that the potassium could go through. And now what he's saying is that the main cause of the potential difference isn't this ratio. It's the fact that the membrane is highly permeable to potassium. So this is very permeable. Potassium can get out if it wants to, much easier than it is for sodium to get in. So what that happens, even if this was a 2 to 2 ratio, it's actually a 3 to 2, but even if this was a 2 to 2 ratio, even though this environment is more positive, you're just more likely to have potassium ions down here bump in just the right way to get across and get to the other side, go against its chemical gradient, right? Because you have a higher concentration of potassium here than over here. So you're more likely to have a potassium bump in just the right way to get through this channel and get out than you are to have a sodium be able to go the opposite direction. And that's what makes this environment. So you have more potassium coming outside because of this permeability than sodium coming inside. And that is what causes, or that's the main cause of the potential difference between the outside and the inside. And so thank you, Stephen Baylor, for that correction. Very interesting.